We travel backward and forward in space. Can we travel backward and forward in time? Metaphysical travel in time as a storytelling device is as old as human beings. Often the journey is told in the form of a dream, usually into the past, as in An Ancient Captivity by Neville Shute, or in the form of suspended animation, usually into the future, as in The Sleeper Awakes by H.G. Wells. The notion of a time machine that transports a person into the past or the future began with H.G. Wells's The Chronic Argonauts, 1888, which was later updated in The Time Machine, 1895. Charles Hinton's writings, positing that time is space-like and exists as a fourth dimension, inspired Wells's thoughts. Since The Time Machine, much science fiction has focused on physical transport in time. Traveling back in time raises problems concerning causality. Events that occur in the past determine what exists and happens in the present. If we travel back in time and alter what once happened, the world would be different on our return. Imagine a world without the ability to create a time machine. Alternatively, if we arrange for the time traveler's parents to never meet, we create a world without the presence of the time traveler. We need not worry. Actual physical travel in time, as presented by Wells and hosts of science fiction writers, is totally and utterly impossible. The impossibility stems not from technical difficulties, but from a misinterpretation of space-time. In The Time Machine, the time traveler shows a circle of friends, a small model of his much larger time machine, in which he later travels. With his friends watching, the time traveler activates the model and sends it into the future. There was a breath of wind, and the lamp flame jumped. One of the candles on the mantel was blown out, and the little machine suddenly swung around, became indistinct, and was considered a ghost for a second. Perhaps as an eddy of faintly glittering brass and ivory, and vanished. Save for the lamp, the table was bare. Where did the time machine go? If it went into the future, it would still be on the table 1 minute, 2 minutes, 1 hour, 2 hours, etc. later. Wells has overlooked that the time machine has a world line. He and all other science fiction writers who explore time travel ignore two unbreakable rules. I. Nothing changes in space-time and all world lines are fixed. Movement along a world line, as in the case of the now, is metaphysical and cannot be physical. It's a story of time travel, and similar stories break both laws. The basic idea of physical transport in time, I, and the notion that a physical object can disappear into the past or the future, violate to be. How can a physical thing, as it travels in time, roll up its own world line and take it with it in a space-time world in which nothing changes? We need not worry about traveling back into the past and creating paradoxes. At most, we can metaphysically travel along our world lines, but nothing can be altered. Kurt Gödel, a mathematician, discovered in 1949 a solution in general relativity where world lines can form closed loops under specially contrived conditions. Metaphysical travel along a world line into the future enables a person to return to the present by moving through the past. It has been used as a popular literary device in numerous tales in which a person trapped in a time loop repeatedly experiences the same sequence of events, as in the comedy Groundhog Day movie. In all these tales, the trapped person remains fully aware of the cyclic repetition. Is this possible? Able. A person's thoughts each time around the loop are repetitive. If the trapped person is unaware of the time loop in the first circuit, then the person remains oblivious in the second and third circuits because of repeated identical events. Therefore, trapped individuals are oblivious to their situation. In many instances, the trapped person alters the sequence of events and successfully escapes from the loop. How is this possible? Is this scenario possible when world lines never change? Is this possible when world lines never change? Philosopher-scientists in the 6th and 5th centuries BC identified two basic aspects of time. Being, which refers to the Parmenidean continuity aspect where time stretches from the past to the future, and becoming, which refers to the Heraclitean transience aspect, where everything is in constant change. These aspects remain unreconciled in both language and science today. Time extends continuously from the past to the future, the aspect used in the spacetime of physics. And things change in time, the becoming aspect omitted from spacetime because it cannot be spatially sized. By family failing to separate these two aspects of time, we constantly encounter the Augustinian riddle. How can things change over time? In the 5th century BC, Alea refuted the notion that the senses can attain truth. He is best known for his paradoxes of motion, which attempt to prove that all apparent change in the sensible world is illusory. Only thinly do the states of being exist. All states of becoming are an illusion, as illustrated by Zeno's paradoxes. Zeno's various paradoxes are similar, the most well-known being the race between Achilles and the tortoise. Pose. The tortoise has a 100-meter head start, while Achilles runs at a speed that is 100 times faster than the tortoise. Achilles runs the 100 meters. The tortoise moves 1 meter. While Achilles runs 1 meter, the tortoise moves 1 centimeter, and this pattern continues in infinite steps. Although Achilles always gets closer to the tortoise, according to Zeno, he never reaches or overtakes it. In this case, the paradox is usually solved by showing with infinitesimal calculus that the infinite number of steps occupies only a finite value of time. And Achilles is hence able to reach and overtake the tortoise, as observed by the senses. Many philosophers still debate Zeno's paradoxes. What is at issue is the assumption that time is continuous and infinitely divisible. Moses Maimonides, a Jewish scholar of the 12th century, discussed atomic time in the Guide for the Perplexed, and referred to a resolution of Zeno's paradox originally proposed by the atomists. Resolution divides time into infinite, indivisible, atomic intervals. An hour is divided into 60 minutes, the minute into 60 seconds, the second into 60 parts, and so on. At last, after 10 or more successive divisions by 60, time elements are obtained, which are not subjected to division and, in fact, are indivisible, just as is the case with space. Motion is, therefore, not continuous, but consists of a series of small jerks, like motion in a movie, and Achilles can overtake the tortoise with jerky movements. Maimoni Aristotle, like most Arab philosophers, greatly influenced him, leading him to oppose the atomists' philosophy. He explained that the mist theory of time implies the creation of the universe not once but repeatedly within each atomic time interval. In the 10th and 11th centuries, Al-Kalam, a rebel school of Arab theologians, rejected the Aristotelian philosophy that underpins Orthodox Muslim theology. The Mutakallimun, the scholars of Kalam, used the atomic theory of the Epicureans from the Greco-Roman world to demonstrate that the world completely depends on the will of the supreme being, the sole agent, atoms. They said that voids separate them, and that the sole agent, Bilan, determines their configurations. Ibn-Basra, who lived in Baghdad and died there in 1013, suggested that time is also atomic. In each atom of time, the sole agent recreates the world in a slightly different form. The worst creation of the world occurs not once, but repeatedly. The Carr theory attributes all explanations solely to the sole agent, excluding any contributions from the natural world. No forces bring the dead material world to life. Despite this scientific attitude, the Kalam theory effectively reconciles the dual aspects of time. In each now, or atom of time, the material world stretches away in space, and memories of the past, and anticipations of the future stretch away in time. Thing exists in a state of static being. This state of being solved and a new state of static exist in a new atom of time. Transient acts of becoming transform whole states of static beings. Shorn of its extreme theology, the Kalam theory accounts moderately well for our complex time experience. The Kalam atomic theory of time harmonizes time's extensive and non-extensive properties. This suggests that we need a new theory of time in which the conjugate aspects of being and becoming play equally important roles. At this point, we should remember that physics advances by modifying and discarding old ideas that were once mistaken for reality. More than most scientists and physicists, they know the impermanence of theories. Many express uneasiness when hearing philosophers, biologists, and psychologists discuss the nature of time in the physical world. If, in the future, we succeed in changing the nature of physical time in a way that incorporates its dual or conjugate aspects, then, undoubtedly, the physical universe and cosmology will greatly change. The following are some extracts from the first chapter of Wells's The Time Machine, where the time traveler explains how time travel is possible to his friends. There are 4 dimensions, 3 of which we refer to as the 3 planes of space, and a 4th dimension, time. There is, however, a tendency to draw an unreal distinction between the former 3 dimensions and the latter, because it happens that our consciousness moves intermittently in one direction along the latter from the beginning to the end of our lives. Well, I don't mind telling you I have been at work on this geometry of 4 dimensions for some time. Some of my results are curious. For instance, here is a portrait of a man at 8 years old, another at 15, another at 17, another at 23, and so on. All these are evidently sections, 3-dimensional representations of his 4-dimensional being, which is a fixed and unalterable thing. Our mental existences, which are immaterial and have no dimensions, are passing along the time dimension with a uniform velocity from the cradle to the grave. In these opening remarks, Wells shows clearly that only mental consciousness travels along a physically fixed world line. Very soon, almost imperceptibly, Wells's account of time travel moves from the metaphysical to the physical, from the plausible to the implausible. The time traveler seeks to prove to his friends that time travel is possible. The time traveler held in his hand a glittering metallic framework, scarcely larger than a small clock and very delicately made. "This little affair," said the time traveler, resting his elbows on the table and pressing his hands together above the apparatus, "is only a model. It is my plan for a machine to travel through time. Now I want you clearly to understand that this lever, being pushed over, sends the machine gliding into the future, and this other reverses the motion. This saddle represents the seat of a time traveler. I will press the lever and off the machine will go. It will vanish, pass into the future time, and disappear." And that happened. The lever was pushed, and the machine disappeared from sight in the future. Thus, in only a page or 2, Wells passes from metaphysical time travel, which contradicts no physical principle, to physical time travel, which contradicts the physical principles of causality and timeless space-time. In metaphysical time travel, mental consciousness travels along a world line. In physical time travel, an object travels along its world line and takes its world line. The age-old cosmological debate concerns free will, which deserves thought. Human beings instinctively believe that they have some degree of control over their lives and are free to influence at will events of the external world. But if they are part of the world, they are subject to deterministic laws, and their belief in free will is an illusion. Either we have no free will, we are puppets, and are not responsible for our actions, or we truly have free will, according to principles not yet accessible to rational inquiry. This argument applies not only to the physical universe, but also to all rational universes. Even if we believe in a rational spiritual realm, we cannot escape the dilemma of free will in an indeterministic world, or no free will in a deterministic world. Augustine of Hippo, the architect of Christian theology, promoted the latter and believed in fate. Only two possibilities exist. Either one must believe in determinism and regard free will as a subjective illusion, or one must become a mystic and regard the discovery of natural laws as a meaningless intellectual game. Max Born, Man and the Atom, 1957. If necessary, then it is not a sin. If it is optional, it can be avoided. Pelagius was a British theologian who lived at the time of St. Augustine. He was opposed to Augustinian predestination because it exonerated sinful behavior. His argument in support of free will and individual responsibility, which diminished God's omnipotence, was condemned by Christian authorities and became known as the Pelagian heresy. Pelagius was forced to flee from Rome's hostility. Concerning fatalism, Michael Dummett, in Causal Loops, writes that the fatalist argument was frequently applied during the bombing of London in the Second World War to being killed by a bomb. So applied, it ran like this: either your name is written on any given bomb, or it is not. If it is, then you will be killed by that bomb, whatever precautions you take. If it is not, you will survive the explosion, whatever precautions you neglect. In the first case, any precautions you take will be fruitless. In the second, they will be redundant. Hence, it is pointless to take precautions. According to this common form of fatalism, if an event is going to occur, any action taken to bring it about is redundant, and any action taken to prevent it will be fruitless. If it is not going to occur, any action taken to bring it about will be fruitless, and any action taken to prevent it is redundant. Can fatalism sustain us in times of adversity? The bombing of London in World War II occurred while I was a student at London University, and my impression is that the answer is yes. Does it diminish motivation in normal times? Each society, each generation writes its own history. The past is infinitely malleable and always the victim of personal and national vanities. Distortions and equivocations form the mythologies that we call history. Can history ever be more than we and the historians want it to be? Newtonian space and time were public prop parties, which all observers shared in common. Its intervals of space and intervals of time separating events were absolute. They were the same for everybody. One person in an apple orchard would see an apple fall from a tree and take 1 second to drop 5 meters. Another person in motion relative to the tree also would see it drop 5 meters in 1 second, no matter how fast that person moved. Now, things have changed. The old Newtonian universe, with its ideas on the fixity of space and time intervals, is no longer the universe we live in. Space and time diagrams displaying events and world lines were used in the Middle Ages, and there is nothing particularly frightening or difficult about them. Until the beginning of this century, they were a convenient, graphical way of representing things in motion. Then came the theory of special relativity, and the theory of special relativity emerged toward the end of the 19th century and was brought into final form in 1905 by Albert Einstein's genius. It has stood countless tests and is now used by physicists every day. Yet even nowadays, when we pause to reflect, the theory is as astonishing as when it first emerged. Relativity requires that we abandon the belief that intervals of time and space are the same for everybody. We trade in these two old invariants for two new invariants. The first of the new invariants is the speed of light in empty space, denoted by c. The speed, 300,000 kilometers per second, is the same everywhere and for everybody, and is independent of the observer's state of motion. In 1887, Albert Michelson and Edward Morley found that the speed of light is the same in all directions on the Earth's surface. This was an unexpected result. The Earth moves at an orbital speed of 30 kilometers per second around the Sun, and Michelson and Morley expected to find that the measured speed of light would be c minus v in opposite directions parallel to the Earth's orbital motion. Instead, they found that the speed of light is the same in both directions. As we know, the Sun moves 300 kilometers per second around the galaxy's center. The galaxy itself moves in the local group of galaxies, and the local group moves in the local supercluster. Despite these motions, the speed of light remains the same in all directions. Even at the high particle speeds in high-energy experiments, the speed of light relative to the particles is always c. The fact that light moves at speed c and c is a speed limit for all particles moving at high energy is not astonishing. The constancy of c for all observers, even for observers moving in opposite directions at high speed, astonishes them. A body moves past us at, say, half the speed of light, and relative to that body, light has the same speed relative to us. Even when the body moves at 0.9 c, 0.99 c, 0.999 c, or 0.9999 c. The speed of light relative to it has the invariant value of 300,000 kilometers per second. Physicists of the 19th century thought that space was just an empty nothing, and electromagnetic radiation such as light could not travel through space unless its emptiness was filled with a medium called the luminiferous ether. Waves of light traveling through the ether were much like waves of sound traveling through the air. The observed speed of sound depends on how fast the observer moves through the air. It is even possible to fly faster than sound waves. It was puzzling that the luminiferous ether refused to behave like air or any other medium. The discovery of the invariance of the speed of light killed the ether theory and led to the revolutionary realization that space is more than mere emptiness. And waves of light are more than mere undulations of an etheric medium. Waves of light became an intricate combination of propagating electromagnetic fields. Space, wedded to time, became an intricate physical structure. We no longer dress space with an ether to give it physical reality, for it has its reality that makes the speed of light independent of relative motion. The second invariant is the space-time interval. Intervals of space and intervals of time by themselves are no longer invariant for all observers. Instead, together, they form an invariant space-time interval. Notice that if time is measured in seconds, or years, distance is measured in light seconds, or years. We can use time units to measure space because the speed of light is universal, according to the first invariant. All observers, independent of their relative motion, agree on the value of the space-time intervals between events when determined. Space and time are fused together to form a unified four-dimensional space-time continuum. Observers, in relative motion to one another, have their own private spaces and times, and only space-time is the public domain that all share in common. This new way of looking at the physical world was stressed by Hermann Minkowski in 1908, when he said, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." Two old ideas, the invariance of distances. In space, the invariance of periods in time has gone, and in their place we have two new ideas: the invariance of the speed of light and the invariance of the space-time interval. Once, space and time were previously considered absolute entities. Now, only space-time is regarded as absolute, while space and time are viewed as decoupled dimensions relative to each observer. Albert Einstein, 1879 to 1955, once a student of Minkowski, crafted the theory of special relativity and formulated its algebra. In 1908, Minkowski demonstrated that diagrams of space and time are not merely convenient mathematical fictions, but actual representations of a four-dimensional physical reality. The universe consists of space and time, not just space and time. Spacetime consists of three basic elements: points, events, lines, world lines, and null geodesics, light rays. Brief happenings are events denoted by points in spacetime diagrams. Things that endure, such as observers, are world lines extending from the past to the future. An observer receives light signals from the past and transmits signals that go out into the future. These light signals come in and go out on the observer's light and travel a distance of 1 light second in each second. 1 light second equals 300,000 kilometers. Each point in spacetime has backward light cones. The backward light extends out into space and back in time, and the forward light cone extends out into space and forward in time. Each observer at each world line point has light cones which are similar, no matter the world line's inclination. All information comes to the observer at speeds less than or equal to the speed of light. For example, information conveyed by sound waves travels at much less than the speed of light. Therefore, the observed events must lie inside or on the backward light. The events influenced by the observer must lie inside or on the forward light. Observers in relative motion at the same point in space-time always say events inside or on their backward light belong to the past, and that events inside or on their forward light belong to the future. However, they do not agree on the past. The future ordering of all events outside their light cone. New York Times, one space-time observer in relative motion has world lines inclined to one another. Thus, observers A for Albert and B for Bertha have relative motion, as shown by their inclined world lines. They do not share a common space and time, but have different spaces and different times within spacetime. Obserspace measures time along his world line. Spacetime intervals along his world line are his time intervals, and his space is peripheral to his world line. Similarly, observer B measures time along her world line, and her space is perpendicular to her. A's space is perpendicular to his world line. B's is perpendicular to hers. Unfortunately, we can only show that space is perpendicular to one world line in a single diagram. This is because the sheets of paper on which we draw our diagrams do not have space-time geometry. Much confusion about special relativity results from not understanding that space-time geometry is not our familiar Euclidean geometry of space. Space-time is composed of contributions from B's time and space, and space's time is composed of contributions from A's time and space. Their spaces are composed of contributions from each other's spaces and times. Two events at different events simultaneously in A's space do not occur at the same place in B's space. There is no true decomposition of spacetime into spacetime. According to the rule, space decompositions into space and time are valid and equally real, hence the name relativity. The rules are simple. I, the speed of light is the same for all observers, and I, all space-time intervals are also the same for all observers. The four-dimensional world of space-time contains space-time, world lines, and light rays. Each event has its light cones, and each world line has its space. This is the theory of special relativity, and the algebraic details, often without Minkowski's insight, are found in many books on elementary physics. Quantities that are the same for all observers, like the speed of light and space-time intervals, are said to be invariant. Laws and equations that are the same for all observers, independent of their relative motion, are considered covariant, The Newtonian universe provides simple examples of invariance and covariance. The intervals of space and space are the same for everybody and are invariant. If we are on a ship moving at sea or in a plane flying in the air and tossing a coin, it falls back into the hand exactly as we are standing on the ground. The laws governing the coin's motion are the same in the plane and on the ground. They are covariant and independent of relative uniform motion. Motion at constant velocity is considered inertial, meaning no inertial force exists. A passenger with closed eyes in an automobile traveling at constant velocity cannot determine the speed of the automobile. The motion is inertial. Only when the speed increases or decreases, or the driver steers to the left or right, can the passenger experience inertial forces and know that the velocity changes. In the Newtonian universe, all velocities are relative, and all accelerations are absolute. In special relativity, the laws of nature are covariant in a wide sense. Consider a windowless laboratory that moves freely and at constant velocity. The motion is inertial. If in this laboratory we measure the speed of light or perform any experiment, we always get the same result, independent of the velocity of the laboratory. No experiment can be devised that will tell us the velocity of the laboratory. The laws of nature are covariant, and the same applies to observers in all laboratories moving at constant velocity. In special relativity, the laws of nature are covariant if the observer's velocity is constant. The motion is inertial. Despite the physical structure of spacetime, with the spacetime limit being the same for everybody, we are still not too far removed from Newtonian ideas. Velocity is relative, but acceleration is absolute. An accelerated observer experiences a force known as an inertial force, which is peculiar to the observer and is not shared by other observers of different motion. The laws of nature in special relativity, as in the Newtonian universe, are not covariant for accelerated observers, only for a special class whose motion is inertial, of constant velocity. We shall see in the next chapter that the laws in general relativity are covariant for the more general class of observers who are in free fall. Despite its constant velocity constraint, physicists always use special relativity for accelerated non-inertial motion. The trick is quite simple and comes from Newtonian mechanics. Suppose we are in a laboratory that is accelerated. In our experiments, we obtain results that are not strictly in accord with the predictions of our covariant equations. We do not throw away the results and give up in despair. Remember, a laboratory on the Earth's surface is in non-inertial motion because of the Earth's rotation and revolution about the Sun. Instead, we imagine ourselves moving inertially at constant velocity while studying the events occurring in the accelerated laboratory. The covariant laws, which now hold in our inertial state, tell us the true results and the corrections to be made to the observations obtained in the accelerated laboratory. Physicists constantly use imaginary inertial motion to understand and correct the results obtained in accelerated motion. The geometry of spacetime is not the same as that of a sheet of paper, and generally the shortest distance between two events is not a straight line, speeds close to the speed of light. Spacetime reveals interesting properties when bodies have relative speeds close to the speed of light. Most people find the results as surprising and incomprehensible. How can a space traveler journey in an ordinary lifetime to a galaxy millions of light years away? How can a space traveler return to Earth and find that his twin sister has grown old while he is still young? The answer is quite simple, and springs from the fact that the geometry of spacetime is not a spacetime as that of the blackboard or the sheets of paper on which we draw spacetime diagrams. All the confusion attending special relativity comes from the simple fact that distances between points in spacetime are not spacetime-like distances between points on paper. We are accustomed to the idea that a straight line is the shortest distance between 2 points. This is true in ordinary space, but not in spacetime. To understand why this is so, let us consider the light cones, the paths on which light rays travel. In 1 second, light travels 1 light second in space. For a light ray, this means an interval of time 1/4 interval of space. Therefore, given the equation, the space-time interval between 2 events on light is always 0. Consider a star at a distance of 1,000 light years. Light from this star hurries to us at immense speed across a wide gulf of space, and after 1,000 years it enters the eye. No one can disagree that light has traversed immense space and time intervals. Yet the space-time interval between the eye and the star is 0. Space-time distances along the backward light to all events that send us signals, and along the forward light cones to all events that receive our signals are always 0. This may seem bizarre, but it explains why the speed of light is invariant and forms an upper limit to all material motion. Consider a straight world line connecting 2 events labeled A and B. Also consider the alternative path, ACB, A to C and then C to B, forming the light cones intersecting A and B. The length of each, as drawn on paper, is longer than the straight line, AB. But in space-time, the space-time is 0. The longest space-time distance between A and B is measured along the straight line that passes through A and B. All other paths between A and B that bend toward the light cones are of shorter length. Space-time contradicts common sense, leading to the so-called twin paradox. Time, peculiar to a body, is measured along its world line, and its age is the length of the world line from its beginning. But bent or curved world lines, connecting any 2 points in space-time, are space-time straight world lines. Thus, a person going from A to B via a bent world line, such as ADB, arrives sooner than another person going via a straight line. Both persons measure time with a wristwatch or other physical means, such as the number of heartbeats. And the lapsed time in each case is equal to the length of the world line measured in space-time. Twins in space-time are born together, and their world lines begin simultaneously. But for the rest of their lives, their world lines will follow different paths, and whenever they meet, they will have slightly differ ages as measured by the clocks they carry. Let us suppose that A stays at home all his life and that B travels a great deal by plane during her life and has a more crinkled world line. At a reunion celebrating their 80th birthday, her world line is slightly shorter than his, and she has lived a slightly shorter life. The difference in ages in this example is very small, perhaps as small as 100 microseconds. At extremely high speed, it eventually returns to Earth. Before the journey, the twins A and B were the same age, but when B returns, it is immediately apparent that A is older than B. "You have cheated," says A. "You have gained, and I have lost time." "No, I haven't," says B. "I am younger than you. My heart has beaten fewer times than yours. You have brushed your teeth more times and read more books than I have." The space-traveling twin B experiences periods of acceleration, including deceleration, in her travels. But acceleration alone cannot cause the twins' asymmetric aging. If B takes a second longer journey at the same speed as the first journey, with similar periods of acceleration as previously, the difference in the ages of A and B is greater. Twin B ages less because of travel near the light cones. The greater the distance traveled, the greater the age difference on her return. A is now seen traveling away close to the light. Surely this proves that A should be younger than B. But at half-time, in B's time, B must start traveling toward A, and to catch up with A, travel even faster and closer to the light. Light makes B younger than A when they finally meet. The calculated age difference in A's space and time, or B's space and time, is the same. The technical problems of space travel at speeds close to that of light are formidable and will not be solved immediately. Probably human beings will not experience in any significant way the bizarre phenomenon of asymmetric aging for many centuries to come. However, asymmetric aging repeatedly occurs with high-energy particles. A subatomic particle known as the muon decays in a millionth of a second into other particles, and this intrinsic lifetime is measured along its world line. When a muon moves relativistically, close to the speed of light, it travels a distance much greater than 300 meters before decay. In its own time, measured along its world line, it decays in a millionth of a second. But to us who are not traveling with it, it is seen to decay much more slowly. If faster-than-light travel were possible, this limerick could be true. We could take an interstellar journey and return to Earth any time in the past or future. However, according to current theory, nothing physical can travel faster than the speed of light. If faster-than-light communication were possible, we could perform impossible things, such as sending information back into the past that would change present conditions. Or if faster-than-light travel were possible, we could journey into the past and do impossible things, such as prevent our parents from meeting. Fortunately for us, but unfortunately for science fiction writers, Wellesian time travel is impossible. To simplify the argument, let us go to the extreme and suppose that M-rays, M for mystic, travel at infinite speed. People on Earth and on a distant planet in another solar system communicate by M-rays. The distant planet is at a distance L, measured in Earth's space. Signals from Earth at time t equals 0 travel instantaneously in Earth's space and time. The return signals travel instantaneously in the planet's time and arrives at the Earth in the past. We could send signals back 10 years into the past. By traveling at infinite speed, space-time travelers could return to Earth in the past. Traveling faster than light is impossible according to the laws of physics. Therefore, causality is preserved and the impossible is avoided. Notice that by traveling near the speed of light, one cannot travel into the past using the twin paradox. Signals sent from Earth at instant p arrive instantaneously in Earth time at the planet at instant q, and their return is also instantaneous. In B, the planet is shown moving away from Earth. Signals sent from Earth at instant p arrive at the planet at instant q, and the return signals travel instantaneously in the planet's time and arrive on Earth at instant r, which lies in Earth's past. Signals sent from Earth at instant p travel infinitely rapidly and arrive at the planet at instant q, and the return signals travel instantaneously in the planet's time and arrive on Earth at instant r, which lies in Earth's future. If M-rays existed, we could communicate directly with our descendants and ancestors.